What's up guys, welcome to another DYNA tutorial, and in this video I will show you how to do a Blastwall simulation. So for our reference, we'll try to do the simulation of one of the experiments in this paper by Kumar, which is published in Impact Engineering in 2008. So let's start get going. So first of all, we want to make the Blastwall. So if we scroll down, we want first of all to find the dimensions of our Blastwall. So since this is like introductory simulation and our goal is to do the the blast wall simulation, we will not have this complicated geometry. We will have only a solid plate. So we will not have this honeycomb core. So first we have these dimensions. It is a square blast wall. So when we go to the LS pre-post, you go here, element and mesh, then shape measure, then we don't have a box, we have 4-node shell, so we need to define 4 points. Now if you go here, we have 610 and 610 millimeter. So this video I will try to make everything in meters instead of millimeter like we have done before. We have 610, which is 0.61 meter. We divide it by 2 because we want this to be in the center. So we have minus 0.0, minus 0.05, and the same thing, minus 0.05. We don't have anything in the z, so it is 0. Sorry. So to make it simple, I just copy paste here. Now we change the x to be positive. In the third point, x and y is positive. In the last point, we have y positive and x is negative. So if you before you create, we put the name Blastwall, then create, and you can see this is our shape. Okay, so this is a very rough mesh. So we try to make it 100 here and 100 here, and see, reject, create again, and here we have our Blastwall. So now we accept. Alright, then done. Now after we make the Blastwall, now we need to fix the edges. We go here, model and part, create entity, and here on the view you click on the top view so that we can select the edges very easily. Hold and press on control, then scroll out, zoom out, scroll on the mouse to zoom out while holding the control button. Now we want to make a boundary SPC, special point coordinate. Okay, so the points that or the nodes that we will select now will be fixed. So here we click on create, and then you see here XYZ, RXYZ, RX, RY, RZ, and all of them are ticked, meaning the whatever points or whatever nodes we point right now, it will be fixed in all these 6 degrees of freedom. So we select by area. There are actually more than one method to select. Select by area, then you make a box here, and you see the nodes here are highlighted. I will zoom in to show you. See, all of them are highlighted. So we do the same thing for the other edges or the other side. So this one is fixed and this one is fixed, and you can make this one also fixed, just to make a box. But here I want to show you another method. You click here by edge, and you click on propagate. Now you just click on one edge. See, now the selection will propagate. So I just show you 2 methods how to select the node. Okay, so before you apply, make sure all of these are right, because the edges are fixed, cannot move and cannot rotate. So apply. So now you have them here. you have them fixed. So now you click on none to hide it. Alright, now next we want to create the thickness of the shell. This is a shell element. So we go to here, keyword manager, and click on all. You scroll down until you find section, and under section you take shell. So here we take shell section, then click on new. How much is the thickness? We go here again. If we scroll down, down and down, we will find it mentioned somewhere. If I'm not mistaken, I highlighted that part. Okay, not this one. Should be somewhere here on the left. Okay, I know, just search. Okay, here the baseline for solid experiments, a 12.7 millimeter thick solid plate was used. So it is 12.7 millimeter. Since we are using meters here, it'll be like this. And click on enter. All of them are changed. Then click on accept. Okay. Now we want to define the material. Okay. We go down here, material, and we select material piecewise linear plasticity, which is number 24. Okay. Here we say stainless steel. Click on new. The density is in kilogram per meter cube. So 7833. This is the density. Young's modulus. If we go to the paper here, the properties, you can find it here. Young modulus 200 gigapascal. We have 100 e power of 9. Resistance ratio 0.3. This one. Initial yield stress 300 megapascal. So 300 e power of 6 because it's megapascal. Tangent modulus 2 gigapascal. So here 2 gigapascal e power of 9. Then accept. Okay. Now done. Okay, if we define the material as we define it now, we will not get the result very accurately. We need to define one more thing, which is the strain rate sensitivity of the material. So what is the strain rate sensitivity? We go here in this website or another website. You can see here is the stress strain relationship or curve for single material, but you can see here we have more than one curve, and each one of these curves are at different strain rate. Okay, if we put it simply, we can say that the material behave differently at different speeds. So since our problem is like a blast wall, we have explosive, and it is a very high velocity problem. That's why we need to take into consideration this strain rate effect if we want to get a very accurate result. So we go back here. Now, most people use C and P parameters. Okay, we have just two parameters here so that the strain rate effect is taken into consideration. But in this video, I will show you how to define load curve ID or table ID, meaning I will define something like what I showed you here. I will define one more curve. I will define more than one curve here and put it in the LS DYNA so that the strain rate it's taken into consideration. So we need to define the table, and before that we need to define the curves. So you go up here to define, then define curve, okay, then new. All right, as you can see here, we have, or there is so many points. So if I want to take insert it one by one, it will take a long time. So I will just load XY data. So load XY data, go to desktop. Okay, so these are the stress strain curve of the material at different strain rates. Okay, I will give you the link in the description of this video so you can download all of these curves. So you go down here, you click on this one, open, and then you put it strain rate 0.0002 and accept. Now you have this one. Okay, now we repeat the same thing for the other curves. Okay, so add new, load, we have this one 0.02, again 0.02 strain rate, and then accept. So you can see here, this is the second curve. Then load XY data, strain rate 1, sorry, add, click on add first, load XY data, here strain rate 1, accept, again add, load XY data 100, strain rate 100, rate 100, accept, and the last one, add strain rate 8000, strain rate 8000, then accept, then okay. So we have defined the curves, but one more thing that I have not mentioned yet, these curves are in megapascal, so we need to multiply them by 10 power of 6, so we put it here. Okay, so this one e power of 6, accept. Now you can see they are 2.2 or 200 megapascal. We do the same for the rest. Here also e power of 6, e power of 6, here e power of 6, and the last one e power of 6. Okay, so all of them are multiplied. All of them now in megapascal. So accept that. Now also the next step, also under the define, we go to table, define table here. Okay, so click on new or add. Now we have 6. The table ID is 6. Table we have S strain, stainless steel L04 or 344L. This is the grade of the stainless steel. Okay. Now we insert the first curve. So this is curve number 1, and the strain rate is 0.002. So here 0.002, we put it here, then insert. Now go to the next one, this one, put it here, and it was 0.02, insert. Now number 3, curve number 3, the value is 1, insert. Curve number 4, the value is 100, insert. Curve number 5, the strain rate value is 8000, then insert, accept. Then if you plot, you have something like this. Okay, accept again, just to double check. Now we go to the material definition or the material keyword. Now we have here load curve or table curve ID. Okay, if you click here, you will not find the table ID, but you remember it as 6, so you just put it 6 here, and don't worry, it will work, trust me. Okay, so now we define the section, we define the material. Now we go to the part so that we assign the material and the section to the part. So we have the blast wall, we define it already. Section ID is here, section shell. Just to double check, you click on read here. You can find this is the defined section, and the defined thickness 12.7 millimeter. So everything is okay, done. Number 1. Now material ID, stainless steel, done. Again, if you want to check, you read here, you click on read. You can find all the properties that we defined just now. And done, done. So accept. So okay. All right. So far now we have the blast wall almost ready. Now we want to define the blast load, which is the main topic or the main thing in this video. So if we go back to our paper here, okay, in this paper we have 3 different experiments, okay, but we will do only one. Okay, so we have the blast wall here, and you have the standoff distance, and you have the explosive charge. Okay, I will go down to show you a different figure, this one. Okay, so we have the blast wall here, the test panel. We already defined it. We define the boundary condition fixed in all sides, and now we want to define the explosive charge. Okay, so we have here R, which is the standoff distance. Okay, and in this paper they did TNT charge of 1 and 2 and 3 kilogram at standoff distance of 10 centimeters. So in this video we will only do the simulation for 1 kilogram. So how to do that? We have the command called load blast enhance, okay, or LBE. Where is it? Here, load blast enhance. Okay, so click on new. This is a very straightforward keyword. M is the mass of the TNT, so we just put it as 1. Now this is the coordinate of the coordinate of charge center. Okay, so if we go here, we need to find the center of this charge. Okay, we have the standoff distance, which is 0.1, and we need to find actually the center here. Okay, so we find the center and we add it to the standoff distance, and we will find the center of the explosive charge. Okay, so of course in X and Y should be 0 and 0, because we make this point actually 0, 0, 0. Okay, so now we want to find the Z distance, which is from here. Okay, in this figure, Z going in this direction. We have 0.1 plus the distance, half of the height of this cylindrical shape explosive charge. Okay, so how to find this one? In this paper, they have the ratio of height and diameter equal to 1. Okay, and we have the density of the material, or the material is TNT. We can find the density. So from there we can actually find the volume, and from the volume we can find the height, and we divide it by 2. So here I actually already calculated, and actually half of the height will be 2.6048. It will be like this, 0.046048, but we need to add 0.1, which is the standoff distance. So this one will be equal to what? VO is a time of detonation, it will be 0 because we don't want to wait. Now the units, we are using unit meters, kilograms, seconds, pascals. If you are using different set of units, you need to change this one. Okay, now the blast type. Okay, we are using number 2 because it is a free air burst. Okay, it is on the air. It's not like a surface charge or underground charge. It is explosives in the air, so it is a free air burst. And that's all what we need to define here. And then this one, accept. Okay, now we define the charge. Now we want to define which area is affected by this TNT. Sometimes you have maybe two blast wall. You want only one of them to be affected by the TNT explosive charge. So we go here, blast wall segment set. Okay, this is a very small keyword. Here we have the blast wall, the blast ID. So click here, you have this one. You have one. This one is actually the one that we defined in the step before. Then click on done. Now, segment set ID. We did not define any segment yet. So if we click here, you see segment is not available. Segment meaning the area or the group of surface that will be affected by the blast wall. So you want to create new, of course. How we create new? With new keyword or new entity. Click here, new entity is much easier. Then click on by part, click on here, then click on accept. Then you already have it here, number 1. Then accept. Okay, what we did actually, we just shortcut to this create entity, and we did a shortcut to here, segment. Okay, so now if you want to unhide it, you just do like this. You just unshow it. Okay, so now we define the material, we define the thickness, we define the segment, we define the blast wall. Now we have just the routine things that we need to define, like the termination and the output intervals. So if we go up here to control termination, go down termination. Okay, this is in seconds. So let's say our termination will be 5 milliseconds, 0.005. Okay, or just make it milliseconds. And then the output intervals, database, and then we have binary D3 plot. So 0.0005, which is 0.5 milliseconds. Then accept and done. Now control S to save. Okay, we just save it in the desktop. Okay, say blast all. Okay, then save. Okay, now we open the DYNA manager. We run the file that we did just now. This is the one. Okay, hope there is no mistakes. Okay, good, everything is working. So we just need to wait and see the result. Okay, fine, very good, normal termination. So now we have everything on the desktop. So here D3 plot is a result, so we just drag it and put it here. Okay, so if we want to make it a bit slow, so now we can see this is actually the result. Make it a bit faster. It is very fast actually. Okay, so we want to see actually the deformation, nodal Z displacement. You can see here is 36 to 37, around that value. So now go to history, nodal, click here, a random point near the center. We see the Z displacement, and you can see here that this is the result. You can see it's a very rough. So what we can do, actually, we can increase the output of the interval. So we close this one, we close this one again. So the output interval will increase the value, meaning we need to decrease this one. So just now we just make it 5 or e power of minus 5. We save, Control S to save. Here we click on this one, rerun the last analysis again, and it's done. Okay, now we close again, close this one. If you notice, you don't need actually to close the keyword file in order to open the result. You just need to open in different windows. Okay, so you open again. Now you can see the result actually more smooth and more nice. Here, click on this one, nodal, set displacement, so you can see all the wonderful colors. Again, you can see it's 40, 35 to 37 millimeters. That's the range of the maximum displacement. Okay, here you click on history, nodal, and then you click here that displacement, and you click on a point somewhere almost in the middle. You click on again. Now you can see here the deformation of the blast wall, and this is 0.04 meter, meaning 40 millimeters, and the displacement is between 34 and 39, almost roughly among those values. So you can see here or here 35, and here is 37, and here is 34 again. You click here, this is 37. Okay, so why I'm showing the displacement? Okay, because that's one of the way how we can find that our results are acceptable or not. Because if you go down here, or you go down or up, I'm not sure. Okay, you can see here, this is solid plate profile measurement. This is actually the center of the plate, and 21.5 kilopascal, meaning when we have the this is the impulse load, but if we translate it, it will be like 1 kilogram of TNT from a standoff distance of 10 or 10 centimeter. So here you can see the maximum displacement is almost 40 millimeters, and you can see also in our result we get it somewhere here almost reaching 40 millimeter. Okay, so now we found that our result is quite not very bad. So from here actually we can find all the other results, like the von Mises stress, or the pressure, or if you go here history, you can also find the energy absorbed. So you can find all those things. This is the energy absorbed. Okay, okay, that's all. Thank you for watching, and see you in the next video. Okay, bye bye.